This is Neil from Anabit, and welcome to converting a unipolar signal to a bipolar signal using a summing amplifier circuit. And that's exactly what we're going to cover in this video. Before I get started, I'll just mention check out anabit.co, where you can find content like this around data converters, ADCs, and DACs. We also have open source reference designs related to data converters, and we recently released a new product, Anabit's new AIoT precision logger, so check that out. And if you enter your email address into our website, you can get a newsletter which gives you updates on content, video, and products. All right, let's get started. Okay, so what are we talking about in this video? A lot of times you might be working with a unipolar analog signal, a signal that's referenced to ground that goes up to some type of positive value. Often in applications, you need a bipolar signal. So the idea is if you're working with communication signals, if you're working with process control signals, maybe you're designing a waveform generator and you need a sine wave that's bipolar, or maybe you're working with a laser lockbox. Things like that where you need an analog signal to be bipolar. DACs, or digital analog converters, which you often use to use digital codes to create an analog signal, are often unipolar. So in this video, we're going to look at a circuit that we can marry with the output of a DAC to basically turn a unipolar signal from a DAC to a bipolar signal. We're going to start this video by looking at an overview of a op-amp configured as a summing amplifier. Then we'll look at the complete circuit with a DAC and the math behind it. Then we'll look at a real-world example where Anabit, we have a family of products called the Reflex DAC, uses this method to take our unipolar DAC IC on the board and convert it to a bipolar signal at the output. Let's move on to the overview of a summing amplifier. Okay, for this video, I'm assuming you have a basic knowledge of op-amps and inverting versus non-inverting configurations. If you don't, I'll have a link in the video description to the electronics tutorials website, a great website that has a lot of basics on op-amps. If you are familiar with inverting op-amps, you can see the formula right up there for calculating the output voltage. And it's basically the feedback resistor divided by the input resistor, which I'm calling R1, times the input voltage, and then times again by -1 because it's inverting, right? So that defines the output voltage of the op-amp. Now for a summing amplifier, we just add a second input, or we could add a third or a fourth. For this tutorial, I'm just going to work with 2 inputs, but the idea is you could add multiple inputs if you wanted to. And the idea here is the formula doesn't change much. We're just adding the 2 inputs together. So you can see V out is equal to -1 times the reference voltage divided by R1 times V1 plus the reference voltage, the feedback resistor divided by R2 times the V2. And then if all the resistors are equal values, the gain for each is 1, and those things can drop out, and V out is just V1 plus V2 inverted. But it's important to note the resistors can play a factor, and they're going to play a factor in the circuit we're going to look at soon, where you could have a gain on one of the voltage inputs of 2 or 3, and then the other one could just be 1. So just keep that in mind. Okay, now here is the complete circuit we're going to look at and go over in detail. So we have a DAC, and our DAC has a 2.5 volt reference. And I'm just using that value for example purposes. It could be any reference voltage. Now, typically DAC ICs will either have an internal reference or the reference is built in, or you have to add an external reference to the circuit. But the key point is you need access to that reference for this to work. So you want a DAC that has an internal reference, but it outputs that reference so you could use it other places in the circuit. And you can see this DAC is referenced to ground, so it's a unipolar output DAC. Then we add a buffer amplifier. So this is just a unity gain amplifier or an amplifier with a gain of 1. It's an inverting configuration. So whatever the DAC outputs, let's say it's 2.5 volts, the output of buffer amp, you're going to get a negative 2.5 volts. And you can see I have that node labeled as V1. Then we have our R1 and R2 just like before, but something to pay attention to is R1 is 1K and R2 is 2K. And I should mention R2 is connected to the voltage reference. From our first example, the voltage reference is represented by V2. And then we have our feedback resistor, which is 2K. So we can see that there's going to actually be a gain factor of 2 for V1 and a gain factor of 1 for the reference voltage being fed to the inverting summing amp. Right, so that's our setup. That's the pieces that we need for this to work. Now, let's run through the math of this circuit to see how we can convert our unipolar signal to a bipolar signal. So let's take the first example where we set the DAC codes to all zeros, the digital input DAC codes, and then we get 0 volts out of the DAC. When we feed that to the inverting buffer amplifier, we're going to get 0 volts at V1. That's not too surprising. And then at V2, or the reference voltage, we're going to get 2.5 volts, right? That doesn't change. That's always constant. Now, when we apply our equation, our summing equation that we looked at on the other slide, we're going to get -1 times 2 times 0 volts, which is 0, plus 1 times 2.5 volts. The 1 is basically the gain of 1. So we basically get 2.5 volts, but it's inverted, so we get -2.5 volts. So now we're getting a negative voltage on the output. Now let's look at the other extreme output of the unipolar DAC, and that's 2.5 volts. We started with 0 volts, now we're looking at 2.5 volts. We're entering some digital code of FFFF, right? All ones. Our buffer output is going to be -2.5 volts because it's inverting. So then we can go back to our equation. We got 2 times -2.5 volts plus 1 times 2.5 volts. So -5 volts plus 2.5 volts is -2.5 volts. But then we have to multiply it by a -1 because it's an inverting configuration. So we get plus 2.5 volts. So now we've shifted our signal to make it bipolar. And not only that, we've doubled the amplitude range, right? Because we have that gain factor of 2. So we have a DAC output that was 0 to 2.5 volts, and now we have it -2.5 volts to plus 2.5 volts, right? And I'm just showing the two extremes. Of course, if you set the DAC output to 1 volt or 2 volts or 1.5 volts, you're going to get some output that's linearly related to this new bipolar range. For purposes here, I doubled the amplitude, right? So we went from 2.5 volts peak to peak to 5 volts. Now, if you don't want to do that, you don't have to. You would set R1 to be 2K, so there would only be a gain factor of 1. But keep in mind then you also have to adjust V2 or the reference voltage or things won't work right. So if you wanted to have the same peak-to-peak voltage but just make it bipolar, you would then either have to use a different reference voltage or you'd have to add a resistor divider to basically half that reference voltage, or you'd have to do a fractional gain of that reference voltage. Another thing you could do is you could make that peak-to-peak amplitude even higher than 2 times that, right? And you just do that by adjusting your gain resistors, but then also you'd have to add another op amp and amplify that reference signal to make it higher. So a lot of things you can do to play with that amplitude range. You could also adjust things so that the signal is not perfectly bipolar. Maybe you want a bipolar signal that's not perfectly centered around ground. You could do that as well. So a lot of things you could do as far as amplifying and shifting your signal. Okay, let's look at a real world example. So Anabit has a couple products called the Reflex DAC, and one of them outputs a plus or minus 10 volt signal from a 14-bit DAC. And that 14-bit DAC is a unipolar DAC. It's 0 to 10 volts, but we add this circuit that I just went over to double the peak-to-peak voltage, but also make it bipolar. Right, so here's the setup I'm going to show you an example measurement from. So you can see the reflex DAC, and then we have an oscilloscope probe connected to the output of the buffer amp. So we're getting that unipolar DAC signal that's inverted. We're going to measure that. And then you can see 2 clips, a black and red clip. That's measuring the output of the summing amp or the output of the whole circuit, right? So that's where we should see that plus to -10 volt range. And then I'm just using a simple Arduino Uno using SPI communication and a 5 volt input to power the board and control it. What I'm doing is I'm just generating a square wave signal that goes from the lowest value of the DAC to the highest value of the DAC. So to cover the whole range of the DAC and the output of the summing amplifier. Where here's an image where I zoomed in a little more on the reflex DAC so you can kind of see a real circuit implementation of this. Here is my DAC IC that's creating a 0 to 10 volt analog signal. This is my 10 volt reference, high accuracy 10 volt reference signal. Then this is a 2-channel op amp. So it has the buffer amp as well as the summing amp there. You can see the oscilloscope tip is right on that R1 resistor that I showed from the schematic, or the output of the buffer amp. And then of course, one of the more important things is, and one of the harder to design things, is this DC to DC converter that's a dual output. It takes a 5-volt power in and creates a plus 15 volt rail and a negative 15 volt rail for our op amp, so we know that we can get that full range of plus and minus 10 volts on the output. All right, here's a screenshot from my oscilloscope. The yellow is channel 1. That's connected to the output of the summing amplifier. That's why it's a bigger signal amplitude-wise. You can see the ground reference here. And then channel 2 is where that oscilloscope probe was on that R1 resistor, or the output of the buffer amp. And you can see the ground place here, right? So this signal is either 0 volts or negative, right? That's its range. 0 volts to negative 10 volts. Why? Because the DAC output is 0 to 10 volts, but the buffer amp is an inverting amplifier, so it turns it negative. And then when we have 0 volts at the output of the buffer amp, we're going to have 10 volts from the reference, and then that 10 volts is going to get inverted by the summing amp, because 0 plus 10 is 10. Then we invert it to negative 10, and that's why we're seeing about negative 10 volts here. And then, of course, when the output of the buffer amp is negative 10 volts, or the DAC is at maximum value, we're going to get that value doubled because we have a gain of 2, so it's going to be negative 20 plus the 10 volt reference, that's negative 10, and of course it's inverted for a positive 10 volts. And then, of course, all the values in between fill in all these different voltage levels. Right, so this is an example of that circuit that we just looked at, with the centerpiece being the summing amplifier, where we convert a unipolar signal to a bipolar signal. Okay, that's it for this tutorial on converting a unipolar signal to a bipolar signal using a summing amplifier circuit. If you have any questions, use the comments section below. If you think there's anything I missed, you have anything to add, please use the comment section below. If you like what you see here, please hit the thumbs up and check out Anabit.co. Thank you for watching.